All right, perfect. So, hello everyone. Thanks for joining one of our other, let's say, WSD 20 minutes time domain talks. Today, we're super delighted to be hosting Professor Sebastian Gomez from the University Texas Austin. And he's a time domain astronomy expert. And from what I know, mainly these days, he's dealing with the exotic transients in the Roman Science collaboration and also at the Space Science Telescope Group, if I'm not wrong. And I think that's the gist of it. And Sebastian, please, the floor is yours. Go ahead. We're very
Hi.
much looking forward to your talk today.
Thank you so much for the invitation and for the introduction. Yes, like you mentioned, I am a assistant professor of astronomy at the University of Texas at Austin, working on everything time domain related, mainly explosive transients, but I also work a lot with the Nancy Grace Roman Space Telescope. And today I'm going to tell you a little bit about my research on time domain astronomy in the era of big data. So, there you go. I'm going to start with the fundamental questions of what we are actually trying to answer in time domain. 1 second. There you go. So two of the biggest questions in astronomy, not only time domain, concern stellar evolution and black holes. Stellar evolution deals with how do stars lose mass, which stars explode, and how do they explode, like really trying to understand the life cycles of stars. And black holes, we are interested to know how do they grow, how do they come to be, and how does this affect their galaxies, the galaxies in which these black holes reside. And another big question that has more recently become accessible is doing all of this as a function of redshift, as a function of cosmic history. So we don't only want to know how do stars and black holes evolve now, but how did they evolve since the Big Bang up until now? And I'm here to argue that transients and time domain astronomy is probably one of the most useful tools to answer all of these questions. That is the fundamental question that we're trying to answer. But then the fundamental problem is right in the name of transients. A transient is a temporary event. A lot of things in the universe are eternal, right? A galaxy will be there for millions and billions of years, but transients will only last days, months, some of them even hours or seconds, right? So if we want to find these transients, we need to be very efficient about doing so. Because these, what I'm going to call hidden gems, right, that we are looking for, are the tools that are going to help us answer the questions about stellar evolution and black holes, right? But we're not looking for these hidden gems in a tiny little stream of objects. We are inundated by an insane amount of data right now looking for these hidden gems. So it is a map of all the transits that have been discovered worldwide up until 2024. So this plot is really old by now. I should update it. But you can see the sky is just filled with transits. And I am interested in figuring out which of these thousands and thousands of explosions that we find across the sky are the hidden gems that are going to help us inform our understanding of the universe. Today, I'm going to tell you about two of those hidden gems, superluminous supernovae and tidal disruption events. Superluminous supernovae are the rare core collapse supernovae that happen when very massive stars explode. And then tidal disruption events are the exotic transients that happen when a star comes a little too close to a supermassive black hole and then gets completely destroyed. So first things first, how do we actually go about finding these transients? There are surveys all over the world and in space scanning the sky, going back to the same patch of the sky every 3, every 5 nights, and sending out alerts saying, hey, there's a new thing there, there's a new transient, go figure out what it is. And these are the discovery machines. These are the photometric discovery machines. We are already in the era of big data. These discovery machines are finding tens of thousands of supernovae every single year. That is the white curve you're seeing here. But the hidden gems are in that orange histogram down there. That is the characterization histogram. How many of these explosions that we've discovered have we actually managed to characterize with spectroscopy? So while photometry is cheap and it can tell us how a supernova evolves, how it gets bright, how it dims, spectroscopy is expensive. And this is the one that's going to tell us the actual composition of the thing that exploded, right? So in this case, I'm showing a supernova with some calcium, some silicon. Without spectroscopy, we would not be able to tell the composition of the thing that exploded. And the fundamental problem that we're dealing with is that we only have enough characterization machines to classify about 10% of all transients that we discover. So we have these photometric machines discovering tens of thousands of transients every single month, but we only have spectroscopy to follow about 1,000 every year. Sorry, every year, not every month. And this is only going to get harder because the Vera C Rubin Observatory Legacy Survey of Space and Time just began operations last month, and it's not going to find 10,000 transients every month. It's going to find them every single night, right? And this is a deluge of data that we're going to be getting. Like Fatima said at the beginning, I also work a lot with the Nancy Grace Roman Space Telescope. This is another revolutionary data source. It's NASA's next flagship mission, planned to launch on September 7, 2026. So this is coming up really soon. Roman is an infrared telescope that has the same resolution as Hubble. If you see this little square right there in the plot, that's Hubble. And then the big footprint, that is Roman. That is 100 times the field of view of Hubble, but with the same resolution. And not only that, it's 10 times the speed of Hubble. So it would be able to do a survey 1,000 times faster than Hubble. And one of the coolest things about Roman is that all of the data that it's going to take, whether it's from a public survey or a proposal that you submit, is going to be public immediately, right? The only limitation is the downloading and processing of the data, but all data will be available immediately. And one of the surveys it's going to do is called the High Latitude Time Domain Survey. And this is going to be a high latitude, so away from the plane, looking for all of these hidden gems that I am interested in. So we have Roman and Rubin coming online, current surveys that are just going to make the discovery regime of transients explode. But our spectroscopic resources are going to stay fairly flat. Relevant to the talk is that WST obviously can help with the spectroscopic resources, but we still need to figure out what objects we're actually going to be following up because the landscape of transients is complex. These stellar explosions have wide range of duration. Some of them last a day, some of them last a month, and wide range of luminosities. Rubin and Roman are relatively slow cadence, so they are optimized for mostly slow transients. They're not going to find the super fast things that come and fade within a day. And this is the region where superluminous supernovae and TDEs lie, which is the area I am interested in. So let's start with superluminous supernovae. So superluminous supernovae, like their name implies, are very luminous stellar explosions. They used to be classified based on a threshold, like minus 21st magnitude. Anything brighter than that would be called superluminous supernova. But we've been finding them at below that threshold, so they're now classified under the spectrum. A normal supernova is powered by the radioactive decay of nickel-56. And these supernovae are powered by, at most, a solar mass of nickel, and that's exaggerating. It's usually a tenth of that. So you might think, well, a superluminous supernova might just be the same thing, but with more nickel. Turns out, no, that doesn't work because the amount of nickel that you would need to power a superluminous supernova is like 28 solar masses of nickel, which is an insane number. And more than that, the late time observations that we take limited to less than 0.4 solar masses of nickel. So it doesn't seem that this works. Superluminous supernovae require a different explanation to power them. We think that the leading explanation to power superluminous supernovae is what is called a magnetar central engine. So this is a rapidly spinning neutron star at the core of the explosion that as it spins down, it deposits its energy into the ejecta, powering the bright light curves that we observe, reproducing the spectra that we observe, and being able to explain the late time flattening, the late time observations that we see in superluminous supernovae. But even though it seems that this is how superluminous supernovae are powered, there's still a lot of other open questions in the field. Like how do they relate to other transients? Are there different types? Do they produce a lot of dust, etc.? And in order to answer these questions, we really need to find more of them. And the question that I deal with is how do we find more of them? Because these are rare objects. In any of the transient surveys that I talked about, superluminous supernovae make up about 1.5% of all transients. So if you just randomly select an object, you're only going to have a 1.5% chance of it being a superluminous supernova, which is not a very good way of studying that. This is why I wrote the Fleet machine learning algorithm. It's a finding luminous and exotic extragalactic transients code that will not discover, but take any transient that is discovered, right, from the transient name server, find the galaxy where that transient is coming from, fit its light curve, its duration, peak magnitude, color, etc., and then feed that into a random forest algorithm to determine on whether or not it is a superluminous supernova. What is a random forest algorithm? So this is made of what are called decision trees. So a decision tree is a way to divide objects into classes. So say you had a bunch of goats and cows. You could say, what is the optimal set of questions that I can ask to produce the purest possible sample of goats and cows? So you can say, oh, if they're small, they're goats, but if they're big, they're cows. But what if it's like a baby cow? Well, then maybe if they're small and black, they're goats, but small and white, they're cows. Anyway, you can keep going, but the algorithm will tell you the optimal set of questions of these parameters, whether it's size, color, horns, etc. And at the end, you end up with group one, which is composed of mostly cows. But this is just a single decision tree. It's called a random forest because you use multiple decision trees. So then when you get a new object, you can run it through all of these decision trees. And based on the number of trees that say it's a goat or a cow, you can determine a probabilistic estimate of a new object that you had never seen on whether it's a goat or a cow. Same thing for exotic transients. If you're looking for something that is interesting, this hidden gems, you can write a random forest algorithm that when you see a new object that you had never seen before, you can get a probabilistic estimate of how likely it is to be one kind of transient or another. In this case, we used it for superluminous supernovae. And we predicted that we could find them with about 50% purity or like 50% success rate. We ran the survey for 2 years and we surpassed our expectations. We are finding them with about a 85% success rate. Of the 50 superluminous supernovae that we find worldwide, 21 were classified by Fleet. So the code is working. We are able to more efficiently find superluminous supernovae and take that 1.5% rate to 85%. This allowed us to produce the largest catalog ever created of superluminous supernovae. It's a complete data release of all types or hydrogen-free superluminous supernovae ever discovered. And it's allowing us to answer the questions I posed at the beginning of like, how are they related to other transients, for example, by unveiling a population that lies in between superluminous supernovae and normal supernovae. We call them luminous supernovae. And then we also answer the question, are there different types of superluminous supernovae? And turns out the answer is not really. They just look like one continuous blob. There used to be suggestions that there could be different types of superluminous supernovae, but I think that was just because we just didn't have enough data. All of the data is public. All of it is on GitHub for anyone to go ahead and use the data on superluminous supernovae. These are also particularly useful for the upcoming missions like Rubin and Roman, because since they are so luminous, they can be seen to much further redshifts, right? So if say you wanted to probe the star formation density as a function of redshift, that's the blue curve shown here, the green points is our current understanding using core collapse supernovae. And as you can see, it's limited to a redshift of around 1. After that, it gets a little chaotic. But since superluminous supernovae are so bright, we're really going to be able to go not only to cosmic noon, but beyond to really probe star formation and the IMF as a function of redshift using superluminous supernovae. The second object are tidal disruption events. This is another class of exotic object that is similar to superluminous supernovae in the way they appear, because they are bright, luminous, long duration, but they're physically very, very different things. A tidal disruption event happens when you have a supermassive black hole at the center of a galaxy, and then a star just starts approaching the black hole, and as it starts to get closer and closer, the star gets elongated. It gets spaghettified, and to the point that it gets stretched so much by the gravitational forces of the black hole that it gets torn apart. About half the star gets flung away, and the other half gets circularized into an accretion disk, maybe producing the jets you see here, but definitely producing that bright flare that we observe as a tidal disruption event. And the variety of tidal disruption events is wild. Some of them have hydrogen, some of them don't, some of them have helium, some of them don't, some of them show radio, X-ray, some of them don't. There's wide range of variations. So we've struggled to create a cohesive picture of tidal disruption events as a full population. So in order to answer that question, we go back to how do we find more of them? And again, Fleet comes to the rescue. So we know that Fleet worked for superluminous supernovae, and it helped us find lots of them. So we wrote another iteration of the Fleet machine learning algorithm, in this case for tidal disruption events. So in this case, it's saying that if we look at anything where a probability of 50% or more of being a TDE, we expect to succeed about 30% of the time. That translates to about 1 or 2 TDEs that we could find every month. We just started running this survey, so these results are preliminary, but of the 11 objects we followed up so far, 4 of them were actually TDEs. So that translates to about a 36% purity, which is greater than the 30% we expected. Not as good as with superluminous supernovae, but still much better than random selection, because TDEs are even rarer than superluminous supernovae, making up only about 0.5% of all transients. And finding more of them is not only going to help us answer the question of their diversity and like trying to really create a cohesive picture of what produces TDEs, but they can also act as independent probes of the masses of black holes. This is the M-sigma relation that just relates the mass of the black hole to the dispersion velocity of a galaxy, which is a method used to measure the masses of black holes. But if you have a quiescent galaxy with a black hole that is not doing anything, it's kind of hard to measure its mass. But if it happens to disrupt a star, do something, we can use that to measure the mass of that black hole. And hopefully with Roman and Rubin as a function of redshift to really start to answer the questions about formation of black holes as a function of cosmic history. So preparing for the future. Now that we have tools like Fleet that we know are not only going to be useful, but necessary in the era of big data, we can use it for other things that rather than just immediate follow-up. For example, we can run these algorithms on existing data sets. So in this case, we ran Fleet on all 100,000 transients ever discovered by ZTF to recover a sample of around 100 TDEs that were missed, that are likely TDEs that we never did anything with. So instead of throwing out this data, we can use this to extract scientifically useful information out of data that was never spectroscopically classified. Tools like this are going to be really necessary in the era of LSST, just because we're going to have so many light curves that are never going to get spectra. This is a project being worked on by my OU student, Ray Suitak, who is like currently working on analyzing all of these light curves and trying to extract information from them. I'm going to conclude advertising another piece of work, because all of the data that we're going to be getting from superluminous supernovae, TDEs, Roman, Rubin, ZTF, etc., needs a place to live. So Noah France is a grad student at the University of Arizona working on the Otter. The Otter is a database that we've created where people can go in and upload their data on TDEs or supernovae, and it's supposed to be a transient catalog for all of this data to live in. So this will help us not only have a central repository with like clean data that anyone can access, but also train future machine learning algorithms by having a curated data set, and also preserving continuity, making sure that data is not only accessible, but like properly stored and publicly accessible. The Otter is live. It's a website that you can go to. The link is right there. And right now it's populated with mostly TDEs, but in the future, we're going to be adding much more transients and much more data. Thank you.
Thanks so much. This was a wonderful talk. Very beautiful also with all the gifts of videos and everything.
Thanks.
So, yeah, if anyone wants to, okay, Laurent, do you have a question? Do you want to go ahead?
Yes, so I was a bit curious. I don't know historically how they were the superluminous supernova were detected. Is it because the distance of the galaxy was supposed to be known, and these objects were brighter. And when you
Hmm.
detect, if that's the case, then when you detect supernova, and you don't know necessarily if you have only photometry, maybe you don't know the distance. What are the features which are able to classify those, to distinguish between superluminous supernova with a regular supernova?
Yeah. So is in the historical context, supernovae um, used to be targeted from the brightest galaxies because you're like, well, that's a massive galaxy. We're most stars, so that's likely where supernovae are coming from. But superluminous supernovae don't come from massive galaxies. They come from dwarf galaxies that we were not really looking at. So we really didn't discover superluminous supernovae until unbiased surveys started coming online, like ZTF, that were just looking randomly everywhere. And that's when we discovered them. Well, before I entered the field, but a few decades ago. And how do we tell them apart? The main signature that we see in superluminous supernovae are oxygen absorption lines in the hot continuum. So most supernovae just don't show this, but really it's about its luminosity too. So they have to be bright blue, and if it has that signature W-shaped oxygen absorption line around 3,000 angstroms, that's also a signature only found in superluminous supernovae.
But then how, when you use ZTF or
Yes.
optical survey, how do you, because you don't have a spectrum, and maybe you know they are blue, but you don't know they are very luminous because you
Yes.
don't know the distance.
That's fleet. That's its duration,
Ah,
color, rise
okay,
time, relation to its host galaxy, the color of the host galaxy. We take all of these parameters into account to get a probabilistic estimate of how likely each transient is to be a superluminous supernova or not, based
okay,
on all of those things. Yeah.
okay, thank you.
Other questions, comments? I have a question, curiosity
Yeah.
myself. So most of the TDS that you were showing, spectral wise, let's say they are coming from the visible regime. So
Yes.
how would that be useful for some upcoming missions, like Roman, for example?
Mhm.
Because you have a good estimate of how these spectra look like. Or like, for example, for Euclid, we can also do a spectroscopy. I mean, it doesn't do like that much time domain, but if we capture one of these events, is there like a guideline from visible that can be translated to near infrared or infrared?
So a lot of the transients that Roman is or other high redshift, sorry, infrared missions are going to be discovering are probing the optical to rest frame UV, right? So the spectrum that
Mhm.
we get here would be mostly blue, and you're right. It's going to be a bit of a paradigm shift because we don't have a lot of templates of the UV portion of the spectra for these transients. For the more nearby ones, we can still do optical. That's fine. But for the highest redshift ones, we have to adapt to what we expect those transients to look at. And yes, that's going to be a whole new discovery regime. Yeah.
Right. Which is why it's exciting, I suppose.
Yeah.
Right. Um, Okay, so I think like for us, this was very exciting because WC will be also operating mainly visible. Like we don't know if it's going to happen. Then most probably like we're going to have an NIR arm as
Yeah.
well. But yeah, like I was gonna say. If we don't have any other questions or comments, like maybe we can close the session here. Okay, if not, I think like that's it. Thank you so much, Sebastian, again.
No.
It was a
Thank you so
delight
much.
to host you today. Yeah,
Thank you.
see you
Yeah.
again. See you.
Bye.
Bye. Ciao.
Thanks.